Hello everyone, I am Rajshekhar Paul. Welcome you all to the presentation of our paper on why security defects go unnoticed during code reviews. To investigate this question, we conducted a case control study of the Chromium OS project. Peer code review or code review is a software quality assurance practice. In code review, developers or code authors send their code to their peer to verify that the code achieves adequate quality to get merged into the main code base. The code review can be an iterative process until the code achieves that adequate quality. Peer code review is very effective in identifying bugs before releasing the software. Prior research works also found peer code review as a useful practice in identifying security defects. Code review has also been a key practice in Gary McGraw's Building Security in Maturity model, which has been adopted in many organizations. That's why most of the popular open source software projects, including Android, Chromium, Apache, Qt, they follow mandatory peer code review practices in their software development lifecycle, which means each code change must be manually reviewed and approved by one or multiple peers before acceptance. However, despite having mandatory code reviews, a significant number of security vulnerabilities of those projects have been reported to the National Vulnerability Database. And this thing is happening over the years. For example, we can see the number of reported vulnerabilities of Chromium and Mozilla projects in recent years. So there might be some missing pieces that lead the code reviews to miss those security defects. Therefore, the main objective of this study is to identify the factors that differentiate between code reviews that successfully identify security defects and the code reviews that missed such security defects. With this goal, we conducted a case control study of the Chromium OS project. Case control study is a type of observational study which is popular in medical science domain. In case control study, two existing groups differing in outcome are identified and compared based on some attributes. A case control study is always retrospective. It starts with an outcome and then traces back to investigate exposures or attributes that make impact on that outcome. We follow the similar model for our study, where the cases are security defects identified during code reviews and controls are security defects escaped code reviews. For our study, we selected Chromium OS project because it's a crucial open source project with significant security implications. We identified two types of code reviews. First, the code reviews that successfully identified security defects, and second, the code reviews that failed to identify security defects. To collect code reviews that identified security defects, we adopted a semi-automated keyword-based mining approach from a prior study. Then, after manual filtering and validation, we built a dataset of 516 code reviews that successfully identified security defects. To build our dataset of escaped security defects, we utilize the search feature of monorail-based bug tracking system of Chromium OS project. For each reported security defect, we identified the vulnerability fixing commit. From that, we used a modified LCC-based algorithm to identify vulnerability contributing commit. Finally, from vulnerability contributing commit, we identified code review that approved that vulnerable code changes. In total, we identified 374 such code reviews that missed security defects and approved vulnerable code changes. We have detailed our data collection approaches with examples in our paper. First, we investigated that which categories of security defects are more likely to escape during code reviews. To answer this question, we categorized each security defect under a common weakness enumeration class, which is a standard classification scheme of software weakness types. Our results find that the probability that a security defect will be identified during code reviews depends on the category of the defect. We find that security defects related to the use of potentially unsafe methods, memory or resource leak, improper synchronization of multi-threaded application, and race condition have very high probability of being identified during code reviews. Also, security defects related to integer overflow, buffer overflow, and inadequate exception handling are also more likely to be identified during code reviews. On the other hand, security defects related to information and resource exposure, improper access control, inadequate input validation, incorrect type conversion, and operation on expired resources are more likely to be escaped during code reviews. Next, we investigated which factors influence the identification of security defects during code reviews. With this goal, we collected 18 code review attributes. Using those attributes, we developed a logistic regression model followed by the approach of Harrell Jr. Logistic regression can be very effective in predicting binary classification based on one or multiple attributes. To build the model, we first do correlation and redundancy analysis. We excluded highly correlated attributes so that the model doesn't get overfitted. After this step, we discarded 6 attributes and kept the remaining 12. Then we allocated degrees of freedom to each attribute in such a way that no attribute gets more than 4 degrees of freedom, and total allocated degrees of freedom remains as less as possible from the budgeted degrees of freedom. This would also ensure that the model doesn't get overfitted. After eliminating highly correlated attributes and allocating degrees of freedom to the remaining attributes, we construct our logistic regression model. Finally, we analyze our model. Our model achieved an AUC score of 0.914 and adjusted R-squared value of 0.6375. Our attributes explain 47.21% variances of the model, which can be considered as a significant improvement over the null model. Then we analyze the impact of attributes. We find that if the code review has higher review time, higher number of mutual reviews between the code author and the reviewer, if the reviewer has prior review experience with the source code file that is under review, or if the code change is marked as a bug fix, then the security defects are more likely to be identified during that code review. On the other hand, if the code change under review touches multiple directories, if the source file has higher number of prior commits, or if the number of review comments gets higher during the review cycle, the security defects are more likely to be escaped during that code review. Surprisingly, our results find that the number of prior code review of the reviewer has an inversely proportional relation with the security defects being identified during code reviews. We can summarize that many security defects are escaping code reviews. Our study finds that the probability of identifying a security defect depends on the defect category, time to complete a review, the number of mutual reviews between two developers, and marking code review request as a bug fix have positive impacts on vulnerability identification. On the other hand, number of directories under review, the number of total reviews by a developer, and the total number of prior commits for the file under review have negative impacts on vulnerability identification. Our code entered are publicly available at the following URL. Thank you.
All right, great. Thank you for the presentation. So I am here with Raj, Asif, and Amiyanshu, who are ready to answer your questions about their presentation. I already see a few in the chat, so if you have other questions, please put them in there as we're going, and I'll come in. So the first question is from Mahmoud, who says, can you comment on the generalizability of the results? So this is one case study. What do you think the results would look like? How would they be different or similar in other situations?
Okay, so without further experiment, it's difficult to predict the external validity of such empirical study. So we used Chromium, which is basically written in C++, and it's a platform-based project. So I cannot generalize that it will be, our results will be same for any web-based project or a different project. So it's difficult to predict the external validity.
Okay, great. The next question from Guru, and I think the next question from Mahmoud are similar. How did you handle the problems of false positives? I'm just going to kind of combine them. So how did you handle false positives? How did you validate the VCCs and looking at false positives and all of that?
Okay, so we manually validated all the levels, and we didn't find any false positive. That's one thing. That's why we didn't have to worry about this thing.
Okay. The next question then from Rashmi. In the projects that you study, do you know if they used vulnerability detection tools or how effective their test suites are? So do you know anything about the characteristics of those projects?
Yeah, so Chromium used different static and dynamic analysis tools. So they used CLang for static analysis, and I forgot the name of dynamic analysis tool. So the thing is, we consider the code review which passed the static analysis tool. So that really didn't affect our results. And considering the dynamic analysis tool, Chromium integrated that in the life cycle. I think that's from 2019. And our data was from 2011 to 2019. So which didn't had that dynamic analysis integration. So we couldn't analyze that impact.
Okay. Then the next question we have from Diego. Do the characteristics of the contributors show any influence on the review quality? So for instance, are reviewers more careful when reviewing PRs from external contributors, which could be potential malicious attackers, compared with core maintainers, for example?
Okay, so almost I think more than 90% of the contributors of Chromium projects, they are basically employee of Google. So I don't think that there is any impact for volunteer-based contributions here. And
yeah, so answer the question, actually, we did not make that distinction because, again, as I said, that even if we have analyzed maybe like among these 600 or 700 data points, maybe like only handful, like 5 or 6 data points would be from external contributors. So that would not give us any statistically significant result. So that's why we did not go through that analysis.
So I have a couple of questions then, and if there's others that people have, please put them in the chat. So why do you have any explanation or any thoughts about why certain CWE categories were missed during code review? So is there something maybe inherent in those types of problems that made them more difficult to detect in code review?
So if you look into the CWE categories, we actually discussed it in the paper. So CWEs which are very easily identifiable, like it just depends on the local context. For example, if you look into unset methods, you just look into that code, that is statement, and you immediately know that, okay, this is vulnerable or not. Or integer overflow, just look into the calculation. So vulnerabilities that you can look into, that's like a local context, like only a handful of lines of code that are very easily identified during code reviews. But identification of vulnerability, that takes a lot of knowledge, and you need to look into multiple files, APIs, a lot of these different things. Those are more likely to escape. Again, this is due to like people. This issue was also discussed in Alberto's paper, expectations and outcomes of code review, and they say that due to the lack of time, code reviews often identify superficial issues. So similarly, things like happens to be in the vulnerabilities that which identification does not take much time are more likely to be identified during code reviews, but which will take a lot of time or knowledge, are more likely to escape due to code reviews.
Okay, great. There's another question here from Guru. How did you classify the CWE types? Are they arranged in parent-child relationships between the types? Did you treat them in a flat or a tree manner? So basically, how did you pick the CWE types?
We manually check each code segment and identify which type of flaws is present in that code. And based on that flaws, we map that in CWE. Then from CWE tree, we level that with that higher level of CWE IDs.
So actually, initially when we did the analysis, we treated the lowest level, I think the child. But after we curated the data set, and we found that I think it was like more than 76 different type of CWEs were there. And it was very difficult to do analysis and present in the paper. So then we considered the higher level parent categories. So for the analysis in the paper, we treated the top level 15, the parent ones. And is that correct, Rajesh?
Yes.
Yeah. But we have in our data set, which is publicly available, we have the both level. So the lowest child level and the parent level, both level is marked in our data set.
Okay, so I have one other question about the, so you had a list of the attributes that about the reviews that help people find these security vulnerabilities. Actually, let me go to the question from the chat before I ask mine. What kind of support do you believe can be provided to code reviewers to improve the situation? So checklists, tool analysis results, et cetera. So how can we help people do better at code review in this area?
So our recommendation is basically for project maintainers or project managers. So there was a previous paper that said that no method is perfect. So every method will identify some defects, and every method will meet every type of like bug identification method. So we say that, okay, if you are using code review, you can expect that this will happen. So this type of vulnerabilities will more likely identified, and this type of vulnerabilities are more likely to be escaped. So to identify these other categories of vulnerability, you should adopt other practices. And that is one thing. And another thing we found that like bug fix commits, people are more careful, and those are greatly carefully reviewed, and vulnerabilities are more likely to be identified. That means like when it's just a new file or a new change, like a new feature, these vulnerabilities are more likely to escape. So maybe reviewers, they need to be more careful about these changes, because these vulnerabilities are more likely escaping. We also found that experience, it does not matter. So like you have thousands of thousands of code reviews, it doesn't help in identifying security vulnerabilities. Also, like
so I'm sorry, I'm going to cut you off because there's 10 seconds left. There's still more questions in the chat. In 5 seconds, this session will close. There'll be a pop-up for a discussion room. Please feel free to go there and continue this chat with the authors. Thank you for your participation.